World first, Na노크랙 regulated self-humidifying membrane fuel cell design inspired by cactus. For the first time in the world, a team of researchers led by Professor Lee Young-moo of Hanyang University developed sulfonated hydrocarbon polymer membranes without a fluoropolymer backbone. Their design has tremendous implications that can have profound impacts on fuel cell research. Not only does this new design reduce costs by approximately 90%, it also enhances conductivity at high temperatures compared to existing sulfonated fluoropolymer membranes. The research paper entitled Na노크랙 Regulated Self-Humidifying Membranes has been published in the UK journal Nature in April 28, 2016. In humanity's search for alternative resources to fossil fuels, hydrogen fuel cell vehicles are one of the most promising energy solutions to power the next generation of vehicles. Modern fuel cells are made of multiple layers of bipolar plates and membrane electrode assembly, which is composed of anode, membrane, and cathode. The layered MEAs are stacked to generate power through the electrochemical reaction of hydrogen and oxygen. Hydrogen, the basic fuel that is channeled through the cathode, reacts by oxidation with a catalyst, loses one electron, and turns into a proton. The electron is used as electrical energy to drive the car, and the proton that goes through the membrane conducts reduction reaction with oxygen that enters through the anode and produces water as emissions from the vehicle. Thus, the membrane and its qualities are critical to the fuel cell process. Remarkable prospects of this team's discovery is that it has overcome the limitations of previous fuel cell membranes. This research could be the key that unlocks the possibilities for the most viable fuel cell membranes that are efficient, resilient, yet affordable. A major obstacle in existing technology is the lack of stability in polymers for use in fuel cells intended for high temperature and low humidity operation. Sulfonated fluoropolymer membranes are used only between 80 to 90 degrees Celsius due to low thermal stability, but hydrogen fuel cell vehicles reach 120 degrees Celsius or higher while driving, so an extra cooling device has to be installed in the engine room. Also, while driving, ionic conductivity of sulfonated fluoropolymer membrane is maintained only when the membrane contains moisture or water. Therefore, an additional external humidifier should be installed in the fuel cell stack, which makes the fuel cell device rather complicated. Another challenge is that fuel cell stacks are incredibly costly. Platinum, the rather expensive catalyst material in addition to sulfonated fluoropolymer membranes used in commercial fuel cell stacks, result in an incredibly costly price tag that is unfit for the mass market. Inspired by the remarkable properties of how a cactus stores moisture in arid desert climates, Professor Lee and his team found a solution to the above challenges. They succeeded by coating the low-priced, non-fluorine-based polymer membrane with plasma-thin films of 10 to 100 nanometers. When moisture is applied, the na노크랙 on the surface of the membrane opens, absorbs, and stores the water inside. When there is not enough moisture, the na노크랙 on the surface of the fuel cell membrane closes, and the moisture inside the membrane is retained. As a result, high hydrogen ionic conductivity can be maintained. In other words, the na노크랙 acts as nanovalves similar to the functions of stomata in a cactus. The experimental results achieved high proton ionic conductivity through na노크랙 self-humidifying membrane at high temperature and relatively low humidity, even in prolonged operations. As for plasma treatment on membranes, room temperature plasma process that has been widely adopted in the industry could be conducted easily.
Distinguished features of the newly developed fuel cell membrane include lower temperature ranges and affordable price. Unlike existing sulfonated fluoropolymer membranes that decomposes at high temperatures above 120 degrees C, the na노크랙 self-humidifying membrane can secure long-term stability without any reduction in electrical performance in high temperature and low humidity conditions. This pioneering discovery also maintained the same performance levels in lower temperatures or below 100 degrees C. To meet the needs of a potential mass market, these membranes are also surprisingly inexpensive, almost 10 times lower than its previous commercialized product. This exciting research has far-reaching implications that applications in residential fuel cell systems, reverse electrodialysis membranes, and membranes for energy harvesting to the development of affordable hydrogen fuel cell vehicles.